Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this tutorial video, we'll go through this AQA topical series. This is for the A Level chemistry, AQA curriculum, although the contents within are entirely suitable for any students doing the 16 to 18 years old curriculum. So in this question, number 3, so we have this question about Maxwell-Boltzmann distribution. So what Maxwell distribution is about is it's an energy distribution. It shows you how the energy is distributed among the particles, among the molecules. This is for a gas. So we have the energy on the x-axis, and then we have number of molecules having that certain amount of energy on the y-axis. So which one represents the mean energy? So if you think about it, this thing with the highest amplitude, highest number of molecules, the largest number of molecules having this energy. So this thing is not necessarily the mean. So what we have there is what you call the mode. So the mode means the biggest number of occurrence. So this is the most frequent occurrences. But then when you look at the diagram, you will see that a lot of the molecules, there is a larger area on the right hand side. That means a large amount of molecules having this much energy greater than the mode, which means that the average of the mean energy is not really going to be the one where you have the most number of particles having this much energy. The mean energy is most well represented by this value C here, which is just a bit bigger than B, because this is going to be, the mean energy rather than this being the mode. This is what you call the mean energy there. So C is going to be the best option possible there. Question number 4, so Maxwell-Boltzmann distribution again. So what does the area under the graph represent? So the total area under the graph means you integrate, that is a mathematical term. You integrate the graph from infinity to 0 in terms of the expression showing you the distribution of energy among the particles. So the total area under the graph will tell you the total number of particles. So say that this D here is activation energy for the reaction. So however many particles that have energy greater than or equal to EA, this area under the graph shows the proportion of the total number of particles, the proportion of particles having enough energy to react. That is what you call effective, or you call it successful collision, because they have overcome the activation energy. So the total area under the graph is simply the total number of particles there. So option B is the best answer there. Question number 5, so we have this thing which is called a disappearing cross experiment. This cross at the bottom of the flask disappears because of the formation of a solid precipitate. This is precipitation of sulfur. It's a redox reaction where you have thiosulfate, that is sodium thiosulfate, containing S2O3 2-, reacting with H+, that's going to result in the formation of sulfur solid, and then you have SO2 gas, and I think you have H2O liquid as well. I mean, you can try and balance this equation. I don't know, I think that is 2H+ there, and then 3 oxygen, and the charges balance, so that's the ionic equation there. So the key idea there really is the solid is insoluble. The gas is going to escape as a gas, obviously. So this is the precipitation that's going to obscure the cross at the bottom of this flask. So which one is likely to decrease the accuracy of the experiment? If you rinse the flask with acid, so you will always have a little bit of acid remaining. If you have a little bit of acid remaining, let's see. I have a feeling that A is probably the one that's going to decrease the accuracy, because we are saying that what happened to the rate of reaction as we have different mole of the acid, since we have a little bit of acid left over. But let's just go through the rest of the option. When you stir the solution, that's okay. That's ensure equal mixing. You want to ensure that the solutions are mixed thoroughly. So that one shouldn't affect your answer, so cannot be B. Using the same piece of paper, so you should, because sometimes the cross are of different sizes. So this is same cross of same size. So how about D? Using different measuring cylinders to measure volumes. So we are still using measuring cylinder. Measuring cylinder is not going to be the most accurate apparatus in the world. So when you use different measuring cylinder, they are still measuring cylinder. They are not going to be very accurate. In fact, you should use different measuring cylinder because these two reacts. They react when mixed. If you use the same measuring cylinder to pour out the required volumes, they're going to react together. So I think so between A and D is going to give you a reaction, a side reaction inside the measuring cylinder. So if they already react when you use the same measuring cylinder, so you don't want to do that if you use the same measuring cylinder, so you should use a different measuring cylinder. That's not going to decrease accuracy, that's going to make it more accurate. So A is going to be the best possible answer there. When you use a different measuring cylinder, that is good, that is going to be a lesser error, so it's not going to decrease accuracy, it's going to improve accuracy instead there. Question number 6. Now you repeat this experiment. Just now you did it at 20 degrees Celsius. Here you also did it at 20 degrees Celsius. Just now you use a 200, well now you use a 250 cm3 conical flask. Just now you use a 100 cm3 conical flask. So this one is a bigger conical flask. If you use a bigger conical flask, it has a bigger base. So the one at the bottom, so the base is bigger. This is bigger base at the bottom. If the base is bigger, so that means the depth is not as deep, so the depth is lower. So that means the solid precipitate, if I prove my point, okay, so let's say this one is now using 250 cm3. Just now you were using 100 cm3. So your precipitate was going to be formed over a smaller surface area. Here is over a larger surface area. Because your depth of solution is not as deep as compared to when you had 100 cm3 flask, therefore it's going to spread out the precipitate, which means that it's going to take a longer time in order for you to obscure the cross that is underneath, because it's not as deep anymore. So time taken will definitely be increased, and that's a result of the solution depth not being very deep anymore due to the bigger surface area. So it's going to take a lot more sulfur to be precipitated out in order to fill up the space there and obscure the cross underneath it. Question 7, this is more of A2 reaction kinetics. So in this kind of topical question, they have mixed up a little bit of AS and A2 here. This is about the initial rate method. So this kind of table are very, very popular. It's about comparing what happened to the initial rate when I change the initial concentration of A and B. This is to work out the order of a reaction. Order of reactions defined as the power to which you must raise the concentration of A, which we write in this square bracket A. So this is the power. This is called the order with respect to the concentration of A. And then concentration of B in square bracket to the power B. This is the order with respect to the concentration of B, where A and B are reacted. We're going to use this experimental data. So if you want to get the order with respect to A, you don't want the B to change. So I'm going to compare experiment 1 and 2. So experiment 1 and 2. So that is when the concentration of B is constant. So what happened when you increase the concentration of A? As the concentration of A increases, as you could see, by how many times? 0.36 divided by 0.12, that is times 3. What happened to the rate of reaction? This is times 10 to the minus 4. This is times 10 to the minus 3. So rate also increases. The question is, it increases by how much? Just now we divided the second by the first. Here we also need to divide the second by the first. So 1.89 times 10 to the minus 3. Dividing that by 2.10 times 10 to the minus 4. So just pressing that onto your calculator. And I get 9. So when I triple the concentration, the rate doesn't just become triple, it becomes triple in a square. So this is equal to 3 square. So therefore we say this is second order because there is a power of 2. This is a second order with respect to the concentration of B. So we have the power to which we must raise the concentration of B there. So that thing there must be equal to 2. Alright, so comparing experiments, what's the next one we do? Oops, excuse me. So here we could compare 1 and 2 because B was constant here. But if we want to get the order with respect to B, we should be looking at constant A, but we don't have that choice here. So what could we do here is, I could do, let the rate be rate constant, concentration of A to the power of A, concentration of B squared, because I literally just obtained second order with respect to the concentration of B. So that is now my rate equation. So what I could do next is, I could potentially get rate, let's say rate 3 over rate 2. I cannot use 1 and 2 again because these B have the same concentration. So I want to find the order with respect to A. So I need the A to be changing, I think. Yep, so because we're comparing ratio. So if I do 3 and 2, so rate 3, there's 3.78 times 10 to the minus 3. Beg your pardon, there should be minus 3 up there in the table. And then this is 1.89 times 10 to the minus 3 at the bottom. We look at the expression, so K on top. Concentration of A for experiment 3, 0.72 to the power of A, and 0.13 to the power of 2. At the bottom, we have 0.36 concentration of A to the power of A, and then 0.26 to the power of 2. That was the concentration of B to the power of 2, as we already obtained second order with respect to B. You could see that the K and the K, rate constant, they do actually cancel each other up. We turn up not needing the value at all. So that is 2. And then I'm going to combine the thing with the power of A together. And then we're going to get 0.13 divided by 0.26 squared. Hopefully you should be able to see this is times 1, this is times 2. So 2 is equal to 0.72 by 0.36 is 2. 2 to the power of A. And then I get 1 over 4 because 2 squared is 4. So 2 to the A is 2 times 4. So 8 is 2 to the A because I moved the 4 up there. So it's multiplied together. So 2 to the power of something give you 8. Therefore A equal to 3. So what we can say is the rate is equal to the rate constant. Concentration of A raised to the power of 3. Concentration of B squared, as that was the first thing I got from the earlier part of the question. Did they ask for the rate equation? Deduce the rate expression there. So I gotten the order. I've gotten the order. So the first part, the second part, and now the third part, get the rate expression. What else do they want? That's all they want, to be honest. So that's it for that 3 marks question there. Now we gotten this table 2 result, and this is 2 experiments, and this is at a constant temperature. This is between C and D. We have this rate equation which is shown here. So this is second order with respect to the concentration of C. And then this is first order because they don't show you any number there. Doesn't mean it's to the power 0. If it's to the power 0, they will not show you at all because anything to the power 0 is just 1. So use the data to calculate a value for the rate constant. So use the data, number 1, deduce the unit of the rate constant. So what I could do is I could, let me see. All right, okay. So K, I will make K the subject. So I'll move the C square and D to the bottom there. So there's rate divided by concentration of C square and then D. So I'm going to use this particular experiment 4 result. So that's 7.2 times 10 to the minus 4. Dividing that by 1.9 times 10 to the minus 2, the whole thing square. Then 3.5 times 10 to the minus 2 to the power 1. So it's a bookkeeping exercise. Make sure you know how to press your calculator correctly, as well as very quickly, and without making any mistake at all. So I got 56.98. Looking at the data in the question, 1.9 2 sig fig, 3.6 2 sig fig. So again, these are 2 sig fig. So it looks like all the data are 2 sig fig. So I'm going to leave this final answer to 2 significant figures. And gotta work out the units. So in terms of the units, what do we have on top here? We had the rate, mole per dm cube per second. So mole, I should probably just write down the unit there. Mole per dm cube per second. Dividing that by mole per dm cube, the whole thing square. And then mole per dm cube for the concentration of D. What we're gonna do next is we're just gonna cancel out mole per dm cube and mole per dm cube. And then we're gonna bring up the mole square, bring it up, become mole minus 2. dm to the power minus 6, bring it up, become dm to the power 6. The s minus 1 remain like that. And just like that, you get the units of the rate constant. So rate constant unit has no particular meaning. Physically, they don't have a meaning. It's just that you work it out as a bookkeeping exercise, and that's how they give you a few extra marks in exam. Part C, calculate a value for the initial rate in experiment 5. You have just gotten the value of rate constant. So for experiment 5, I could get the rate is equal to the rate constant. So I'm going to use 56.98 so that it's more accurate value instead of the rounded value. Multiply by the concentration of C, so it's 3.6 times 10 to the minus 2 square, 3.6 times 10 to the minus 2 square. What else do I have? 5.4 times 10 to the minus 2. That is to the power 1. So just multiplying everything together and giving your final answer to 2 sig fig based on the data in the questions, 2 significant figure. I get 3.988 times 10 to the minus 3. Don't forget, 2 sig fig, 1, 2. Appropriate number of significant figures is based on the data in the question. That was given as mole per dm cube per second. So pretty straightforward for that 1 mark. Should be an A level A2 question there. And part D, the rate equation for reaction is this: rate equal to rate constant times the concentration of E. Explain qualitatively, so not using calculation. Not using calculation, why doubling the temperature has a much greater effect than doubling the concentration of E. So what does raising temperature do? And what does doubling concentration do? Okay, so effective collision or successful collision is basically it refers to those collisions of particles having overcome the activation energy, because if you don't overcome the activation energy of a reaction, you're not going to be successful collisions. So in terms of temperature, as temperature increases, so what happened to the Boltzmann diagram? The Boltzmann diagram, which describes the energy distribution of particles, there will be more particles. There are more molecules having energy greater than or equal to the EA, therefore more successful collision or more effective collision. So essentially, there are a lot more particles having enough energy to react there. So what about raising concentration? So concentration is just to do with the number of particles. You don't change the amount of energy at all. There are more particles, there are more molecules of E in the same volume, so there are more of it because mole per dm cube, right? So there are greater number of particles, greater number of molecules per unit volume, but all of them still have the same energy. So you still get the same proportion of effective collision. So it's still the same proportion of effective collision. So the rate is not drastically increased because there is no change in the molecular energy distribution at all, unlike with temperature, where the whole Boltzmann distribution will have changed its shape. The last part of this really long question, this slow reaction has this rate constant. Use this equation. When you see this equation, hopefully you can see the relationship for a straight line graph. So that is your y, that is your y-intercept. This is your gradient, and 1 over t is your x-axis. So if you plot ln k against 1 over t, where t has to be in Kelvin, then your gradient is minus Ea over r. Calculate activation energy. This is in kilojoule per mole. When you see the unit of r, this is in joule per Kelvin per mole. And therefore that Ea calculated will be in joule per mole. Later on, which we convert to kilojoule per mole by dividing by 1,000. So use this equation. So what do we know? We don't have a graph. So what can I do? Yeah, ln of 6.51 times 10 to the minus 3 is equal to ln 2.57. Oh, I tell you what, I should probably rearrange the equation first because that is actually the easier thing to do. So I'm going to move EA over RT here. ln A minus ln K. So EA equal to RT ln A minus ln K. So I've just rearranged everything and now I can just sub in everything. So there's 8.31 multiplied by the temperature which is already in Kelvin since this one is per Kelvin. So I multiply by that. Remember that this is joule per mole, sorry, joule per Kelvin per mole, and multiply by Kelvin. Kelvin and per Kelvin cancel, and I'm just putting in all the values. So ln of 2.57 times 10 to the 10 minus ln of 6.51 times 10 to the power minus 3, and we do a square bracket. Not too sure how well that appears on your screen, but that's the best I could do. And just press your calculator. You're going to get a positive number because activation energy, positive value for almost 98%, 99% of a reaction, of any reaction. And I get like 29.004 for this expression here. Multiplied by 300, multiplied by 8.31. Oops, I think I pressed my calculator incorrectly. Just double checking something here. Okay, multiply by 300, multiply by 8.31. So I got my value, 72307. As you can see the unit, follow the mathematics, the physics, that is joule per mole. You want it to be in kilojoule per mole. So you divide that by 1,000 and you're going to get plus 72.3 kilojoule per mole. I gave my answer to 3 significant figure simply because you look at the data in the question, 2.57, 3 sig fig, 8.31, 3 sig fig. So my final answer there, plus 72.3 sign value unit for your for what you learned from energetics topic, sign value and unit, activation energy. That's it for that 12 marks question. That's it for this short tutorials on Redox reaction, which encompasses a little bit of AS chemistry or Maxwell distributions and quite a lot of A2 order of reactions, reaction kinetics, and this kind of activation energy calculation. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry, at ptet.chemistry on Instagram, Facebook, Twitter, then Telegram to get connected. Don't forget to get in touch at plus 673. There's the country code 673 8656158 to get in touch for private tutoring, where I tutor any examination board series. To be honest, I can go through concepts and go through questions of your choice there. Thank you for watching again. Hear from you soon, and hopefully the tutorials help you in your learning of chemistry.